Hi, I'm Avinash Paliwal, and I'm excited to present our work done in collaboration with Leia Inc. Implicit view-time interpolation of stereo videos using multiplane disparities and non-uniform coordinates. We present an approach for view-time interpolation of stereo videos. We build upon X fields and propose to handle this application by performing a per-scene optimization using an implicit network. Specifically, given pairs of input view-time coordinates and their corresponding frames, we optimize an implicit network by minimizing the loss between the estimated and input frames. After the optimization, and during inference, we can pass any arbitrary coordinates to the network to generate the view-time interpolated video. We make two major contributions to address the challenges of the system when handling stereo videos: multiplane disparities and non-uniform coordinates. Since we would like our system to be deployed on embedded devices, our proposed approach should satisfy three constraints. The inference must be real-time, the model should not use significant storage on top of the original video, the model should be memory efficient. Next, I will discuss the options available for stereo view-time synthesis and whether they fulfill these constraints. A large number of existing methods propose to handle this application using various scene representations, such as multiplane images and neural radiance fields. However, these techniques often violate one or more criteria. For example, MPI-based approaches have a significant storage overhead and large memory cost. On the other hand, nerve-based techniques have slow inference speed. Different from these techniques, Pemano et al. Proposed an implicit model called X fields capable of performing simultaneous view-time light interpolation. Specifically, this approach optimizes a coordinate-based network to learn an interpolatable implicit mapping between the input coordinates, view and time in our case, and the observed images. Instead of generating the RGB frame directly, XFIL uses the network to generate flows at the coordinate of interest. These flows are then used to warp and blend the neighboring images to synthesize the interpolated output. This approach satisfies all of our constraints, as it can perform inference in real time, does not have significant storage overhead, and has a small memory footprint. However, it produces results with poor interpolation quality on stereo videos because of two major problems. First, in cases where the two views have large disparity, like the one shown here, the network is not able to properly interpolate the flow. This negatively affects the quality of interpolated views. Note that when performing stereo view synthesis, the 2D flow can be represented by disparity. Second, natural videos captured using handheld devices are shaky and contain motion spikes. This plot shows the average optical flow magnitude in each frame of the video, and as seen, there are motion spikes in two locations. Using normal uniformly distributed coordinates, the model is unable to accommodate the large motion spikes, leading to severe artifacts in the interpolated video. To address these issues, we propose multiplane disparities and non-uniform coordinates. I start by discussing our proposed multiplane disparities. I'm going to explain our representation on the synthetic scene containing three objects. The numbers inside the objects show the disparities between the left and right views. The network is only optimized using the left and the right views, and should be able to interpolate the in-between views. However, as discussed, it will have difficulty interpolating the objects with large disparity, like the circle. To address this issue, we propose to use the network to estimate multiplane disparities, where the disparity is represented using a series of planes, each at a specific predefined disparity. For example, here we have three planes at disparities equal to 0, 40, and 80 pixels. Each plane contains objects with the disparities in the vicinity of the plane's disparity. Note that these planes are estimated in the canonical view. To reconstruct the disparity at, for example, the left view, we shift each plane according to the view coordinate and the disparity of each plane. The shifted planes are then combined to produce the left disparity. Similarly, for the right view, the network estimates the multiplane disparities at the canonical view, and the final disparity is reconstructed by shifting and combining the planes. As seen, since the network estimates the multiplane disparities in the canonical views, the disparity between objects in each plane is small, making it easier for the network to perform the interpolation process. Here we show the multiplane output for a real example. The network generates a multiplane output where the objects are barely moving. These planes are shifted based on the disparity levels and merged using a pixel-wise max operator. As you can see, the interpolated output is a high-quality disparity map. Now let's discuss our solution to the motion spikes. I will explain our proposed solution with a 1D example. Here, the colored dots represents the relative pixel movement at different coordinates, basically giving us the pixel's velocity. For uniform coordinates, the model tries to fit a smooth curve through the dots and fails to accommodate the motion spike, shown by the green dot. We propose non-uniform coordinates, where each pair of frame in the video sequence is separated from the others. This allows the network to fit all the points. The unused regions in between the sequences allows the network to smoothly ramp up and down to the motion spikes. We show the visual comparisons on a real example. For uniform coordinates, the interpolated video contains significant artifacts and the video jumps during large motion spikes. Our approach using non-uniform coordinates generates a smooth interpolated video. Now let's take a look at some of the results. We show a few comparisons here, but more visual and numerical results can be found in the paper. We show some numerical comparisons on two light film video datasets, Centel and LFVID, containing 5 and 6 videos respectively. We augment the MPI approach using the state-of-the-art video interpolation approach, film, to allow for both view and time interpolation. Our approach significantly outperforms the other approaches across all metrics. Here we show some visual comparisons. The NeurFlow approach lacks details as it directly estimates the RGB output. Film plus MPI output contains artifacts during view synthesis. XFields has severe artifacts around the foreground objects. Our approach generates high-quality interpolated videos. In conclusion, we present an approach to generate novel view time frames from an input stereo video. We make two key contributions. We propose multiplane disparities to handle objects with large disparity, and we introduce non-uniform coordinates to accommodate motion spikes. We demonstrate that our method significantly outperforms the state of the art. Thank you.